Hey you, welcome to all of you my dear friends on your favorite channel, that is JE Physics Maniac. So we have gathered here for one more time to discuss few good questions on electric field, and I'm planning to have another session with some of the beautiful questions on the application of Coulomb's law very shortly, right? So I hope you have enjoyed the previous videos, and I hope you are studying very carefully, rigorously and religiously. And remember one more thing, that is, it is only your effort which will be counted at the end of the day. So be very honest to yourself. I know that we are entering a generation where everything is available, right, with a click of mouse. So whenever a question is presented in front of you, it is more important to think on those questions, pause the screen and try on your own, taking your copy or tab, whatever you want, rather than just typing the question to find the solution available for internet. And it is a cancer which can kill you, literally. I mean, I do believe that if your career is killed, then it is killing a soul. So I want all of you to become successful, fly with all colors, and definitely all my dear friends will cruise to the altitude of success. I don't have any doubt about that. So let's start. So at this question, I will just tell all of you, pause the screen, try your own, then go for the solution. So there is a simple pendulum of mass m, carries a charge q in it, length of the pendulum is given as L. There is a uniform electric field in the region, calculate the time period of small oscillation for the pendulum about the equilibrium position in following cases. In this case, E is vertically down, it is vertically up, it is horizontal, and in the other case, it is directed upward, making an angle of 45 degree with the horizontal. So we'll take cases one by one. So case 1, they are saying that there is an electric field vertically down. So if I just draw the pendulum, I'll see that in this case, let us say that this is the bob of the pendulum. It is hanging from here. This is the length L. Downward direction force acting is mg, and they have said the field is also downward, and this is equal to mg by q, as this is having a charge plus q, so there will be an extra charge of qe, correct? And this qe is also equal to, if I do qe here, it is just like mg. So what is the net force acting in the downward direction? So if I write tension is here, so T is equal to qe plus mg, which will become 2mg. I hope this is clear to all of you. So if it is done, then what we can write from here, that G effective is basically equal to 2G. So time period capital T, so I will write time period because I have already written tension as T. So time period is equal to 2 pi root under of L by 2G. All right, fine, clear. Now let us go for the second one. So what is they are giving in the second one? Second one, they are saying that the electric field here in this case is acting upward. So I will take the upward electric field, no problem whatsoever. So there is a pendulum. This is downward force acting, mg. Upward electric field is there. What is the value they have given? They have given 2 mg by q. So there will be an upward force acting which is equal to qe, that is equal to 2 mg. So in this particular case, we can comfortably write what is G effective now. G effective is equal to 2 mg minus mg, which is equal to G. And if it is G, then time period capital T will become 2 pi root under of L by G. So we have solved first and second case successfully. In the third case, what they are saying, that there is an E which is horizontal. All right, no problem, we will do it. So if there is an horizontal electric field, suppose in this direction electric field is there, or I will take a little bit below here, no issue. This is E, right? And the simple pendulum is in that direction. It is hanging like this. Fine, this is the point of suspension. Here is the bob, and downward force is mg, as the field is horizontal, so there will be a force acting horizontally in this direction. that will be equal to QE. Now the interesting fact here is that they have given this QE is also equal to mg, right? So if it is the case, then the resultant force will be in this direction. So if I think about the pendulum will be like this. All right, fine. And this is the force that is acting in the downward direction, that is mg. This is the force acting in the horizontal direction, that is qe. And if I join them vectorially, I will get a resultant like this. But this is not required because we are champion to do this basic vector. This qe is also equal to mg. And if I take the resultant force out here, then the resultant force in this direction, so T effective will come root under of QV square plus mg square, or we can write G effective is equal to root 2 into G. So if it is root 2 into G, then time period, here in this case, we can write 2 pi root under of L by root 2 into G. So case 3 is also solved, right? So what is case 4 given? Let us check that there is electric field of magnitude, and I think there is a mistake. It must be like E is equal to mg by q. The same field I will take here also is directed upward, making an angle 45 degree with the horizontal. We will do it. Let's check. So in this case, there is an electric field like this. All right. So I have taken electric field like this. This is E, and the pendulum is like that only we are taking. All right, fine, right, no problem. So here in this case, what will happen? We will see that this electric field basically will have two components. One is this component, this is Ex, so force will be Qex, and in that direction we will have force equal to Q into Ey. Downward force, it will be mg. So F net along y will be mg minus Qey, and F net along x will be simply equal to Q into Ex. So the vector sum of these two will be the resultant force. From there, we can easily figure out what is G effective. So if I want to calculate the G effective here, so that means for the pendulum in this direction, there is a horizontal acceleration, and that acceleration will be equal to Q into Ex by m. There will be a vertical acceleration that will be equal to G minus Q into Ey by m. So in this particular direction, we will have G effective. G effective will be equal to the vector sum of these. So we can write Qex by m whole square plus of this entire term, that is of G minus Qey by m whole square. So then time period will be equal to 2 pi root under of L divided by this term over here, that is root under of Qex by m whole square plus of G minus Q into Ey by m whole square. So we have successfully tackled all the four cases, correct? This is quite easy, not much difficult. So I hope you have understood. Let us go for the next one, right? Okay. So now you see, they are saying that there is an electric field which E is equal to minus Bx plus A exists in a region parallel to x direction. And the first thing that we'll notice here, that here it is given E is equal to minus of Bx plus A. So basically this is a non-uniform electric field. That means the electric field is changing with respect to x. No problem. So a charge is released from origin x equal to 0. So firstly, what we will see here, that force acting on the charged particle can be written as q into E. So can I write q into E means minus of bx plus a. So this is equal to, what can I write? This is equal to mass into acceleration, right? And you have to figure out that acceleration of it when the speed becomes 0. So we have to figure out the position x value where the speed becomes 0. So now if you write, see here, if you write a is equal to dv dt, if you write dv dt, then you are going to engage two variables. One variable is already present as x, another variable is present as t. So we should not go in a direction which includes two variables. So if I want to cut it short, we know that a can be expressed as v dv dx. So that only I will write here. So a is equal to v dv dx means we are going to m q by m of minus of bx plus a. So this is the acceleration that we are having here. So now if I just segregate v dv is equal to, we are going to get minus of q by m minus of bx, this, I hope this is, there is no minus, it should be plus only, that of dx. Now if I integrate, I will definitely get the value of v. I will integrate the result from 0 to v as it is starting from origin. Okay, and this is 0 to x simply. Okay, fine. So if I do, what is the result I am getting? That is very interesting. So we will get minus of bq by m, integration of x dx will give you x square by 2 plus of this, we are getting aq by m into x. This is equal to v square by 2. All right, so this is the equation of v that we got. Let us say this is equation number 1. All right, so what we want acceleration when v is equal to 0. So if I now make, so from equation 1, if I make v is equal to 0, then I will get the value of x. So what is the x value we are getting? We will get bq by m into x square by 2 is equal to aq by m into x. So what is the x value we are getting? X value we are getting, I think this is 2a by b. Yeah, so x is equal to, we got 2a by b. So once we got the value of x, if I feed this value of x into this equation where we got a, that is here, we can comfortably get the value of acceleration, right? Again, I am leaving the calculation is up to you, so that I want you people to be engaged. You can do the last calculation, fine. And if you check that this x equal to 2a by, if you substitute here, bb will be cancelled, minus 2a, I can directly check your answer. If it is coming, a is equal to minus of q into a by m. So this is the final answer that you will get. All right, easy question, not much tough. Let's move on. Now here in this particular case, as you can see here, the statement, you read the statement carefully. What they are saying, that there is a uniform horizontal electric field of strength in a region. A pendulum bob is pulled to make the string horizontal. That means initially it was here, it is pulled from this position to the horizontal position. So immediately whenever it is being pulled from the horizontal position, from the vertical position to the horizontal position, the thing that will move in my head, what are the forces under which it is moving? So there are two forces. That is how you have to attack the question. One force is gravitational force, and another force is electrostatic force. All right, fine. So if it is moving from this point to that point, initially it was at rest, so I will take E is equal to 0. Finally also it is coming at rest, so V is also equal to 0. So if I apply work energy theorem, What can I write from here? I can write work done by gravity plus work done by electrostatic field is equal to change in kinetic energy, which is equal to 0. So it means work done by gravity is equal to minus of work done by electrostatic field, or vice versa. It means we can also write work done by electrostatic field is equal to minus of work done by gravity. That's fine. So let us calculate what is the work done by gravity. All right. So now they are asking what? Find the maximum angle theta naught that the bob swings before coming to rest momentarily. Right now, that is interesting. Why it is interesting? Because they are not saying that the bob is coming to rest at this particular point. So it is coming to rest in between somewhere. Let us say here. And here this angle is basically theta naught that they are asking us to calculate. So no problem if I take this point as x, a, and this point as x. So we will apply work energy theorem between point A and x. No issue. So let us calculate the work done by gravity and electrostatic force between point A and x. So if you see this scenario, since gravity is acting in the downward direction, that is the direction of action of gravity. So we have to calculate the work done against gravity, we must concentrate only on this displacement, the vertical displacement. All right. So if it is L, then one thing is quite clear, that we can calculate this position. Fine. But if you go back to this question once again, then you have to think again and again ki what practically is happening, how the things are happening. You see here they are saying a pendulum bob is pulled to make the string horizontal and released. Correct? So that means the string, the pendulum is released from here, not from this occasion. So it was pulled from this, it is made horizontal, then it is released. So whatever the line of thought we are having, now we have to alter. So what we have to do, if this point is B, so now we have to apply work energy theorem between B and X. So see, I'm showing you all possibilities that if you do not read the question properly, where you can get stuck and ultimately how you can end up in getting the wrong answer. Right? So ultimately we understood that we have to apply the work energy theorem between B and X, not between A and B, not between A and X, but actually between B and X. So now come. So if I redraw the diagram, this is the horizontal position. From here it is coming down, here it is at rest. This is theta naught, this is L, this is also L. So now I will bifurcate. So you check here, that is L sine of theta naught, and if I talk about this horizontal distance, it is simply L into 1 minus cos theta naught. So when it is swinging down, you see work done by the gravity is positive and work done by the electrostatic force is basically negative. Why so? Because it is falling down means gravity is acting in that direction, so force and displacement in the same direction, but electrostatic force is acting in the horizontally rightward direction and the particle is going back, so the work done by electrostatic is negative. I hope you have understood. So what is work done by gravity? That is simply mg into L sine of theta naught. What is work done by electrostatic field? Tell me. That will be QE into L 1 minus cos of theta naught. So now if I manipulate the values here with a minus sign, it will be there because it is negative. So I can write, since work done by gravity is equal to minus of work done by electrostatic field. So I will be able to write mg into L sine of theta naught is equal to minus of minus QE into L 1 minus cos theta naught. So this minus minus will be plus. So mg into L sine theta naught is coming to be plus QE into L 1 minus cos theta naught, we can write it as 2 sine square theta naught by 2. And on the left hand side, mg into L sine theta naught can be written as 2 of sine theta naught by 2 into cos of theta naught by 2. So that is equal to QE into L 2 sine square theta naught by 2. Ultimately everything will be cancelled, so we will get tan theta naught by 2 is equal to QV by mg, and theta naught will be equal to 2 tan inverse of QV by mg. So that will be the ultimate answer. See, the fallacy with this question is that now I will discuss what you could have been done wrong with this. What you could have been done wrong, you will see, sir, since the pendulum is at rest, so then force due to electrostatic is equal to force due to mg. So we will just equate them. So after equating the forces, it is in that direction like this. So I will write, sir, you see, I will be very happy, this is T. So if this is theta naught, then this is also theta naught. So this is T cos of theta naught. This is T sine of theta naught. This is mg, right? Okay. So if we check the result here, I think sine theta by 2 cancel. Here is a change actually in the value. We will get the actual value will be mg by qv, not qv by mg. So we will get just a small change. This is mg by qv. This is also mg by qv. Anyway, so the thing that I was discussing now is that if I do it like this, then we will end up in writing T sine theta naught is equal to mg, sir, and T cos theta naught is equal to qv, sir. So tan theta naught is equal to mg by qv. Then theta naught is coming to be tan inverse of mg by qv. All right. So this, the answer you could have perceived. This is the answer you could have perceived, right? But actually what you are getting? You are getting 2 tan inverse. Why? Because of one small usage of word this. So you have to be careful. Right? I hope you have understood. This is quite clear to all of you, right? The next question is, find E if the bob comes to rest when the string is vertical. So when the string is vertical, then it is very simple. So for part 2 of the question, when the string is vertical, theta will be equal to pi by 2. So if theta is equal to pi by 2, then I have written tan theta naught by 2 is equal to mg by qv. So in that case, it will be tan of pi by 4, that is equal to mg by qv. So that is equal to 1. So in that case, E will be equal to mg by q. That's it. Okay. So this is quite easy, not difficult at all. Fine. Let's move on. Yeah. So now next there is a question, and this question is a little bit different question to what we have solved already. So here in this case, they are saying that there is a plane, and this plane basically there is a pendulum which is hanging. In case 1, it is exactly like this. So I will just quickly tell you, in this case the electric field will be in this direction, And you have to remember one thing, that here the electric field due to this plane, and they have given large horizontal dielectric sheet, so non-conducting it is, so you have to remember the value, which is sigma by 2 epsilon naught. So this is the value of the electric field, that only this is the only case you have to remember. So in that case, what will happen? In the first case I am discussing, downward force is mg, upward force is basically qe. All right, so in this case G effective will be equal to mg minus qe, fine, divided by m, total force by acceleration. So G minus q by m. E means I already told you, sigma by 2 epsilon naught. So here in this case t will be equal to time period 2 pi root under of L by G effective means G minus q sigma by 2m epsilon naught, and that will be your final answer for part 1. Now what happens in case of part 2? In case of part 2, this diagram you see, the field now is not exactly vertical, it is little bit different. So I will just quickly draw the diagram. Have patience please. So in this case, this is the plane in which positive charges are kept like this. So it is assumed that the electric field now will be in this direction. So this is the direction of electric field. And what is the situation in case of that pendulum? That pendulum is now basically in this configuration. So let us see. So in the downward direction, what is the force? mg. In this direction, what is the force acting? That is equal to qe. All right, fine. And it was initially like this. Don't you think it will be pulled away by this horizontal force? This will be qex, and in the upward direction there will be force of qey. So because of this, the pendulum can no longer be in vertical position. Actually the pendulum now will be like this. So here is the point of suspension, let us assume. So now here is the point of suspension, fine, and this is the angle alpha that they have given in the question, alpha. And if you notice that this inclined plane angle they have given to be beta. If this is beta, we have to remember this is also beta from simple geometry, so this is also beta. All right, fine. So let us check key what is the net acceleration that we are going to have. So we can write g net along y is equal to g minus q into ey by m. So that is equal to g minus q into ey. Ey is nothing, that is already sigma by 2 epsilon naught, and this y component is cos component, so I will take this as cos beta divided by m. G net along x is simply q into ex by m, so that is equal to q into sigma by 2 epsilon naught, this is sine beta divided by m. So what is the G effective now? G effective will be equal to, it will be a big term, root under of G minus q sigma cos beta by 2m epsilon naught square plus of q sigma sine beta divided by 2m epsilon naught square. So this is G effective. Once we get the value of G effective, next thing is what? Simple, T equal to 2 pi root under of L by G effective. So this is somewhat little bit different, correct? I hope you could understand. So this is another application. Let us go back quickly to this question. In one part, there was a surface which is completely horizontal, so it will be giving electric forces to this charge in the upward direction. And here in this case, in the second case, is a little bit different, as this is the direction in which electric field will be applied, which will be divided into two components. In the downward direction, mg will be there, so thereby getting the net acceleration, effective acceleration, and we will get the answer. All right, fine. Okay, let's move on. So this is the last part, this is the last question we will discuss today. So once you pause the screen, quickly read the question, what they are saying. That is a uniform non-conducting ring M and radius r, 2 point charges q and q prime are fixed on the circumference at a separation of root 2r. So they are saying this separation is root 2r. So that is very, very significant out here. Why? Because if I draw the ring, then the 2 points are chosen in such a way, one point is here, this is q, one charge is there, this is the center, and another charge is at this point, this is q prime. So this angle they have said to be theta, and this they are saying to be root 2r. So if I take this angle to be theta prime, so I can comfortably write theta plus theta prime is equal to 90 degree. That's important. All right, theta plus theta prime is equal to 90 degree. So that we have to take care of. Fine. The ring remains in equilibrium. Now that is important. So I have already told, if a system is in static equilibrium, then summation of F acting on the system will be 0. That is point number 1. And point number 2, summation of torque, net torque acting in the system about any point inside the system will be equal to 0. So quickly I will take you through the guided tour. Electric field is vertically upward, so this upward force on q prime is how much? We can write q prime into E. There is q, so what is the force acting here? That is equal to qe. Downward force, total mass of the system, into g, so I can write q prime into E plus of qe is equal to mg. This is equation number 1 that we got from force is equal to 0. Now we can get another equation. What is that? That is net torque is equal to 0. So that is pretty easy. So you check here that from this, I'll just take here. So here in this case, this is q charge, so the force acting is qe. Fine. Here is the center. I have taken, sorry, pardon me, this is theta. So if I calculate this distance, is, if this is r, this will be r sine theta. Now on the other hand, here this is q prime, so force acting is q prime into E. This angle is theta prime, so obviously this distance, as this is r, it will be r sine of theta prime. mg, which is acting through this center itself, so torque due to q prime E must be equal to torque due to qe about the center. Now since we are calculating about the center, so torque due to mg about the center will be equal to 0. It will not be brought into the calculation. So what is the torque this? So force q prime E is the force into perpendicular distance. How much? R sine theta prime is equal to force. How much is the force? QE. What is the perpendicular distance? R sine theta. All right. So what we are getting from here, you see, they have given the value that E is equal to 4 mg by 7q, that they have already been provided. Fine, we are coming to that part later. So if I substitute the value here, I can write q prime into E plus of q into E means 4 mg by 7, that is equal to mg. So from here we'll get the value of q prime into E. How much you are getting? 1 minus this is equal to 3 mg by 7. So q prime into e is equal to, we are getting that value. So now you come to the next page. So q into this is equal to, what can we write? Q prime into e means 3 mg by 7 into sine theta prime is equal to, qv means 4 mg by 7 into sine theta. All right, I hope this is clear. So this mg cancels out, 7 is gone. Now theta plus theta prime is equal to 90 degree. So theta prime is equal to 90 degree minus theta. So if I substitute bluntly, we are getting tan theta is equal to 3 by 4. All right, so this is the answer we were searching for. It's a pretty nice question. Okay, fine. So here, what are the conditions to be checked in? That is concept number 1 that you have to apply. If the system is in static equilibrium, net force acting on the system is 0, as well as net torque acting on the system about any point inside the system is equal to 0. Okay, thank you very much. I hope I was able to entertain you well. I hope that you have learned few new things. Thank you. In the next class, we will be dealing with electric field lines. So do watch out the upcoming videos, and definitely they will be as interesting as ever. Thank you.